Our next section is covering the rational root theorem, also known as the rational zero test. What this does is give us all possible zeros of a function. It does not guarantee any of them will be a zero, but if the function has real zeros, it will be in this list. So here's how we generate the list. Notice we have a function starting with a leading coefficient of a, n is the highest power, all the way down through q, which is the constant. If this function has a zero, it will be in this form, where the numerator of the zero would be a factor of the constant, and the denominator of the zero would be a factor of the leading coefficient. Once we use some actual numbers, hopefully this will make some more sense to you. So our essential question is determining how to apply the rational root theorem in order to find zeros of a function. Starting off with just an example of listing all possible zeros. We start with the factors of q, which in this case is 6, the constant. Positive or negative, because to multiply to 6 or negative 6, you could have a positive 1 times negative 6 or a negative 1 times positive 6. If the 6 were positive, you could have both values being negative. So we always put a plus or minus sign in front of our factors, and the numbers that go into 6 are 1, 2, 3, and 6. Then we divide each of those numbers by the factors of the leading coefficient. In this case, our leading coefficient is 1. So of course, dividing all of these values by 1 isn't going to change anything. So if this function has a real zero, it will be one of the numbers in our list. I have for you here a graph of this function. So as we take a look at this graph, this is scaled by 1. We have positive 2 as a 0, which is in our list, and negative 1, which is also in our list. Notice not every single value in our list is a 0, but the zeros that are part of this function are also in the list. What we're going to do is use the rational root theorem to make educated guesses about how to start dividing functions that we can't factor with the methods that we've learned. So this function is a cubic. It does not factor with the t-chart or the AC method. And since there's only 3 terms, it does not factor by grouping. So we will use synthetic division. We will guess and check based on the list that we come up with from the rational root theorem, and then see if we can continue to factor with the methods that we know. Starting off, our constant is 6, and our leading coefficient is 1, so this is going to give us the exact same list that we got on that first example, all of the factors of 6, positive and negative. So we set this up with our synthetic division, 1x cubed plus 0x squared, don't forget those placeholders, minus 7x minus 6. Then we simply pick a number from the list that we think will work and give it a shot. If it doesn't, if we do not get a remainder of 0, we try again. Typically, I like starting with the smaller numbers. However, in this case, I know that if I multiply the 1 by 1 and add it to 0, I'm still going to get a 1. So I want to find something a little bit bigger, like 2 or 3. I'm going to start with a 3 this time and see what happens. Drop the 1, multiply by 3, drop the 3, multiply by 3, add, multiply by 3, and add. Because we got a result of 0, that means that 3 is a factor of the function. Next, we can rewrite the function in partially factored form. We take that 3, put it into the asylum with the x, make it opposite, write the result. Remember to drop a power, so we have x squared plus 3x plus 2. And now we can finish factoring using t-chart. We get x minus 3, what multiplies to 2 and adds to 3. That would be a positive 1 and a positive 2. And finish finding those zeros using the zero product property. Set each term equal to 0 and solve for x. The first one we already knew, that was the 0 we found with our synthetic division. The second one, we get a negative 1. And the third one, we get a negative 2. Don't forget to write these as ordered pairs because it does link to the graph of the function. All right, let's try that again. This time we have a leading coefficient that is not 1, so let's see how to set that up. First of all, our constant is 12, so all of the factors of 12, plus or minus 1, plus or minus 2, plus or minus 3, 4 goes into 12, 6 goes into 12, and of course 12 goes into itself. The factors of 2 are 1 and 2. Dividing by 1 doesn't change anything, so now I'm going to divide each of these values by 2 to get additional possible zeros. 1 divided by 2 gives me 1/2. 2 divided by 2 gives me 1, which is already in my list. 3 divided by 2 gives me 3/2. 4 divided by 2 gives me 2, which is already in our list. 6 divided by 2 gives me 3, which is already in our list. And 12 divided by 2 gives me 6, which is already in our list. So we have technically 4 additional factors, plus or minus 1/2, and plus or minus 3/2 when we divide by that factor of 2. Setting up our synthetic division, we have 2x to the 4th plus 7x cubed minus 5x squared minus 28x minus 12. Noticing that that minus 12 isn't huge, I want to start with a number that's fairly small, because if you start with a large number, as you multiply by that large number, you're going to get very large numbers. I'm going to try -2 on this one. Dropping our 2, multiplying by -2, adding, multiplying by -2, adding, multiplying by -2, adding, multiplying by -2, and adding. Apparently, I am a great guesser because I did not try either one of these in advance. We got another remainder of 0, so that worked out as a factor. The result of this will be a cubic function. Remember, we're going to drop a power from the 4. So if I have 2x cubed plus 3x squared minus 11x minus 6, I cannot factor that by grouping. Looking at these numbers, 2 and 3 do not have a common factor, and neither do 11 and 6. So I'm going to need to take another guess. So I'm going to set up synthetic division again, ignoring that remainder because that is not part of the result. We do not use that remainder when we rewrite this, adding those variables back in. So I'm going to stop at the -6. For my next guess, I'm going to try -3, drop the 2, multiply by -3, add, multiply by -3, add, and multiply by -3. We get another remainder of 0. Since what we're left with is a quadratic, I'm going to go ahead and write this out. What we have so far for our function, the first value we divided by was -2. I'm going to put that back in with the x and make it opposite. The second value we divided by was -3, going into the asylum with the x. And then our result here, now we have to drop 2 powers because we divided twice. We've got 2x squared minus 3x minus 2. To finish factoring this, we could use the AC method, or if you've gotten to be good at guessing and checking with synthetic division, you could continue to divide this synthetically as well. I'm going to factor this with the AC method to help remind you of how to do that type of factoring. So for just this trinomial on the end here, we're looking at what multiplies to a -4 and adds to a -3. So those values would be -4 and +1. Remember, this is not where you can put those right into the binomial. You need to split that up and factor by grouping. So we have a GCF of 2x from our first 2 terms, and a GCF of 1 from our second 2 terms. Then we have a GCF of x minus 2. Factoring that out, we're left with 2x from the first term and a +1 from the second term. Putting that back into factored form with the rest of the function, we had our x plus 2, x plus 3, x minus 2, and 2x plus 1. Setting each piece equal to 0 and solving. We get x equals -2, which was that first value we divided by with our synthetic division. -3 was the second value we divided by. The other two that also would have gotten us correct answers are a +2 and a -1/2, and writing them as ordered pairs. Here's your U-Try questions. Please attempt this to the best of your ability and come to class with any questions you have on the rational root theorem.